Let's see this. If capital G is a graph with n vertices and k connected components, then what is the minimum and maximum number of edges does G have? So this is asked in one of the GATE exams. They have asked only, I think, minimum or maximum, but anyway we are going to look at both the cases. What is the minimum number of edges required and what is the maximum number of edges required, or what is the present in the graph, not required, present in the graph. Now what I mean to say is, they are saying that totally there are n vertices and k connected components. Then you are supposed to find out what is the minimum and maximum number of edges that can be present in the graph. So let's deal with the case where I want to find out the minimum number of edges required, right? So what is the minimum number of edges required is, in order to find it out, let us assume that there are n vertices and all are isolated initially, right? Like this. In our graph we don't have any edges. Let us say our graph is having n vertices, as they said that there are n vertices, all are isolated, right? Now we have to add minimum number of edges to this graph in such a way that we should produce k connected components there, right? Now how is it possible? It is possible only when by the addition of every edge we can decrease the number of connected components only by 1, isn't it? Therefore every edge addition has to result in decreasing the number of connected components. How is it possible? See this. If I connect these two, then the number of connected components is reduced by 1. Why? There are n minus 2 connected components, right? Each connected component is containing one isolated vertex and one more connected component, therefore it is totally n minus 1, which means by adding one edge I should be able to produce n minus 1 connected components, right? And by adding two edges I should be able, by adding one more edge I should be able to produce n minus 2, right? So how is it possible? So if you connect these two, which means now I have these three in one connected component, and what about the remaining n minus 3, right? So n minus 3 plus 1 connected component will be there, right? Which is going to result in how much? N minus 2. Got it? So try to add every edge, and whenever you add an edge, see that one of the one connected component is reduced, or the number of connected components is reduced by 1. Now you keep on adding, let us say, x edges, right, in such a way that we are going to get k connected components. Now what is this x? Now if we can find out the x, that is the minimum number of edges that can be present in this graph, right? So what is this x? X is going to be n minus k. So what does it mean? By adding x edges you will be able to get a graph with n vertices with k connected components. This is one way of seeing it. Now other way of understanding the same concept is, if you want to get this, let us say you have n vertices. Now you divide it into two groups. One group containing k minus n, k minus 1 vertices which are all isolated, forming k minus 1 connected components. Now the other group will contain n minus k minus 1 vertices, which is nothing but n minus k plus 1 vertices, right? Now in the other group you try to connect them all with minimal number of edges in such a way that this entire thing will become one connected component. Therefore the total number of components will be k minus 1 plus 1, which means k, resulting in a graph with n vertices and k connected components. Now what is the minimal number of edges required to connect a graph with n minus k plus 1 vertices? It is n minus k, right? Because we have already seen the some properties saying that if I have n vertices, then the number of edges required to connect them all, the minimum number of edges required to connect them all is n minus 1. Now in this graph, if I have n minus k plus 1 vertices, the minimum number of edges required will be n minus k. Therefore in this one, finally I get one connected component containing these many edges and all the remaining isolated vertices forming k minus 1 connected components. So you can either understand this way or this way. Got it? Okay, now let's look at the maximum part. One question is what is the minimum number of edges possible, and the other question is what is the maximum number of edges possible, right? So in order to find out the maximum number of edges, you can go in two ways. So one thing is, if you can find out, or if you can make a graph in such a way that it is complete, we are going to have maximum number of edges in that, right? Therefore one simple way is, try to classify the vertices into two classes in such a way that k minus 1 vertices out of n vertices are going to be kept as isolated vertices forming k minus 1 connected components like earlier case, and the remaining vertices, which is n minus k minus 1, so which is nothing but n minus k plus 1, all these vertices should be kept in a separate connected component, and all of them should be connected with as many edges as possible. So when is that possible? Only when you make a complete graph with these many vertices, right? So if I make a complete graph with these many vertices, how many edges will be there in that complete graph? N minus k plus 1 C2. This is the answer, right? So this is the maximum number of edges that can be present in that graph containing k components and n vertices. So this is how you can think about it intuitively. If you want the proof will be like this. Assume that initially all the n vertices are connected by maximum number of edges possible, right? So how is it possible? If you have n vertices, let us say we have kn initially, which means all the vertices are initially connected, all of them are connected to each other with every possible edge. Now from this kn, how many edges, minimum number of edges I should remove in such a way that I get k connected components, right? So out of this nc2, so initially there are nc2 edges. Why? With n vertices, if you want to make a complete graph, then the number of edges present will be nc2. Now out of these nc2 edges, how many edges should you remove in order to form one connected component, or in order to isolate a vertex and make one connected component? It is going to be n, right? So if I delete n vertices, n edges, or let us say n minus 1, see the degree of each vertex in this complete graph kn is n minus 1. Now if I remove n minus 1 edges which are all incident on a vertex, then I can isolate it, isn't it? See, what I mean to say is, if you have kn, every vertex will have n minus 1 edges incident to it. Now even if I have to make one vertex isolated, why should I isolate it? That is the way I get a component, isn't it? Even if I have to make one vertex isolated, I am supposed to remove n minus 1 edges. Therefore out of nc2 edges, the minimum number of edges I should remove in order to isolate one vertex and make two components is n minus 1. So once I delete this, I get two components, right? Now if I want to make three components, then the remaining graph will be k n minus 1. From this k n minus 1, I have to again isolate one vertex. In this k n minus 1, I need to remove n minus 2 edges which are all incident on every vertex, right? So from this one, if I have to isolate a new vertex, I have to delete n minus 2 edges, right? Therefore from this, if I again remove n minus 2 edges, I am going to get one more vertex isolated, right? So at this point, the number of connected components I get is 2. Now if I again delete n minus 2 vertices, the number of connected components I get is 3. Why? 2 isolated vertices plus remaining kn minus 3. Got it? And now if I have to again remove one make one vertex isolated, I need to remove n minus 3 edges, so on. So at this point I am going to get 4 components, right? So on. What is the total number is n minus k plus 1, isn't it? So if I delete these many vertices, I'm going to get exactly k components at this point. So if I delete these many edges, I'm going to get exactly k connected components. Now if I try to add it all, it is going to be nc2, so n into n minus 1 by 2 minus, so how many of these are there? It is going to be k minus 1 into n, so n's are going to be k minus 1 minus 1 plus 2 plus 3 plus so on plus k minus 1, so which is going to be k minus 1 into k by 2. Right, now if you simplify these terms, this entire term, you are supposed to get n minus k plus 1 into n minus k by 2, which is nothing but n minus k plus 1 c2. Right, so either you go in this procedure or you go in this procedure, you are going to get the same answer. So what is this procedure? Initially you are assuming that we have kn, which means a complete graph containing as many edges as possible. From that we are trying to remove minimal number of edges so that maximum number of edges will be present, still making it k components. Right, so every time if you have to make one more component, you are supposed to delete n minus 1 edges first. Why? Every vertex is going to have a degree n minus 1. You not isolate it, you are supposed to remove these many. Now in the remaining graph, again if you have to isolate one more edge, you are supposed to remove one more vertex, you are supposed to remove n minus 2 edges, because degree of every vertex is n minus 2. And again if you want to isolate one more, you are supposed to do this. How many times should you do this? Till you get k components. Got it? Now if you simplify it, you are going to get this answer. So either intuitively this way or that way. Okay, anyway, so this is the maximum number of edges that can be present in a graph with n vertices and k connected components, and the earlier number, which is n minus k, is the minimum number of edges that can be present in a graph with n vertices and k connected components. Okay, so what does it mean? The minimum number is n minus k and the maximum number is n minus k plus 1 c2. Therefore in general you can have the number of edges like this. The number of edges in a graph which has n vertices and k connected components will lie between these two numbers, anything in between them. Okay, fine.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkey's ranking is 400. If you are happy to get into IIT Roorkey, then getting into universities better than IIT Roorkey is easier compared to getting into IIT Roorkey. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities or 50 lakh universities, but whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. and then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.